Hey, welcome to Jed Foster Maths. In this video, we're going to be looking at solving some more tricky integrals and a very good technique that we can use when faced with these integrals. This technique is called integration by parts. And what this is used for is when we have an integral that can be represented like a product or something that we don't have on our table of integrals that requires this technique to solve. For example, if you had y equals the natural log of x. Now we know its derivative y dash equals 1 over x, but we don't have a set way to integrate this. This is where integration by parts comes into play. So the first technique I'm going to be showing you is the more traditional technique, and this way I find takes a bit longer than the second way that I'm going to show you. But the reason for this is I want you to know where these techniques come from and how to use them. So integration by parts, you need to write out a table, just like your product rule and differentiation, but it's going to be a little bit different. You're going to write u, and then you're going to have v dash. And keep them diagonal to each other. That's going to help you stay organized and visualize it. So we need to set one function equal to u and one function equal to v dash so we can integrate this. So when we're trying to integrate natural log of x dx, you can imagine there will be a 1 out the front of that, but we just don't write it. There's always going to be a 1 out the front of ln x, and the same with any constant. So this is how we can solve this. Because there's no set integral for ln of x, what we need to do, we need to use integration by parts. And what this means is we can differentiate one function, then we can integrate the other, and then we can solve for the integral of ln x. And once you've wrote u and v dash, we need to set one function equal to u and one equal to v dash. One function we're going to be integrating, and the other one we're going to be differentiating. Now we can differentiate ln x, we just know that that is 1 over x. So let's say u equal to natural log of x. And then we're going to have u dash and v. And we need to set one function equal to v dash. So this is where it differs a little bit from the product rule with differentiation. We're having u and v dash is what we're originally setting our functions to. So we can set v dash equal to 1. And when we're going to v, we know that v dash or v prime is the derivative of v. And integrating is the opposite of differentiating. So how we integrate ln x to get 1 over x, so you know how we're going to differentiate ln x, that's going to give us 1 over x. We're going to integrate 1, which is going to equal x. So that's all we need to do. One function we're integrating, the other one we are differentiating. So once we've done that, what integration by parts looks like is we have the formula. We're going to have u times v. So our integral, we'll write that as I equals u times v minus the integral of v u dash. So now all we need to do is plug the numbers in. So we can see u times v is going to be x times ln natural log of x minus the integral of v times u dash. So we're going to be multiplying v and u dash. That's going to be 1 over x times x. So that's just going to be 1. And that's all there is to it, because the x's will cancel out. That's how we get 1. And all we need to do is solve this. And we know the integral of 1 is just x. So by using integration by parts, we can now solve this. So we have x ln x minus, now 1 integrates to x. And don't forget to add your constant at the end, plus c. So that's your traditional integration by parts formula. Now the second method I want to show you, which I think is much more efficient and saves you a lot of time in exams, is the DI table. And I'll show you for the exact same function. So we have y equals natural log of x. We're asked to integrate. We're asked to integrate this function. So for this second method of integration by parts, we're going to start off by writing d and I. And in front of the d column, we're going to have plus, minus, and so on. It's just going to oscillate between pluses and minuses. And that only applies to your d column. So essentially we have our differentiating column and our integrating column. So we need to set one function to integrate and one function to differentiate. Now again, we can see there's going to be an invisible 1 times ln of x. So we use the constant of 1. We can integrate that, but we can't integrate ln x. So we set the integral to 1. And we set the differentiating column to ln x. And after that, we go down one step, and we need to differentiate and integrate respectively. So ln of x differentiates to 1 over x, and 1 integrates to x. And as you can see here, we have a row that we can integrate. So this is your one of your 3 stops. Whenever you get to a row that you can integrate, you stop. Whenever you get to a row that has the same variables as your original function, you stop. And whenever you get to a row where the derivative or integral goes to 0, you stop. That's your 3 stops. So for the differentiating integrating table, you stop when a row can be integrated is the same as original function and goes to 0. So screenshot this if you want, but when you're doing this table method, that's when you need to stop, alright? So you can see that when we multiply 1 over x times x, that's just 1 because the x's are going to cancel. So that row we can integrate. And this is where you need to have a keen eye because you need to spot when you need to stop on a specific row. And what this table does pretty much, you have to go diagonal. And you multiply diagonally, so we're going to have plus ln x times x. So that's going to be x multiplied by ln of x. And then we have minus 1 over x times x. And because we're stopping at a row that we can integrate, we're taking away 1 over x times 1, which is just 1 dx. And now we end up in the same position as we did before. So that's going to be x ln of x minus x, and don't forget to add plus c. So that's the table method. That's the method that we're going to be using throughout the video. Alright, moving on to something a little more complicated. Let's say we had the question, we were asked to integrate, let's say, x squared sine of x. Actually, let's make the sine of 2x. And in this video, I also want to show you the reverse chain rule to integration. We've gone over this for differentiation. Now in integration, when you have a function like sine of 2x, the way we can integrate this is by doing the opposite to the chain rule for differentiation. I'll show you what this looks like. So again, we're going to write a DI table, differentiating and integrating, plus, minus. So we're going to differentiate x squared. The reason we're doing this is because we know that that's eventually going to go down to 0, whereas if we were integrating x squared, it's going to be infinite. And we want it to go down to 0 so we can apply one of our 3 stops. Because we know that sine of 2x is never going to stop integrating. x squared differentiates to 2x, which differentiates to 2. Because it's a constant, it goes to 0. And integrating sine of 2x, that's going to become, and again, when we're doing these, because this is the reverse chain rule, we're going to differentiate in, but instead of multiplying, we're going to divide by the inner function. So it's the same, but we're dividing instead of multiplying because we're integrating, which is the exact opposite of differentiating. So the derivative of 2x is 2. And because we're dividing, we're going to write it 1 over 2 times, and sine of 2x is going to integrate to negative cos of 2x. So that's all there is to it. Okay, so next up, we need to keep on integrating till we reach the same row where our derivative goes to 0. So integrating this again, we're going to get minus 1 over, and that's going to become 4 sine of 2x. And the reason it goes to 4 is because we're dividing, you just multiply the denominators together. If you really wanted to, you could have minus a half. You bring it outside, cos of 2x is going to become so exact same thing. If you find this way easier for you, definitely do that. Just taking shortcuts here, but that's why. And then we need to integrate this one more time. And because we know sine integrates to negative cos, the negatives are going to cancel out, leaving us with a negative 1 divided by, we have 4 times 2 cos of 2x, and 2 negatives cancel, positive. That's just going to be 1 on 8 times cosine of 2x. And as you can see, we've reached a row that is 0. So all we're going to do, we're just going to multiply it diagonally down, and this is going to solve our integral. And you just keep going till you can't anymore. So integral, we'll call it f of x equal to, that's going to be negative x squared on, sorry, that's going to be negative x squared divided by 2 of cos of 2x. And you have a minus here and a minus there, so they're going to cancel out, giving you a positive, plus 2x over 4 sine of 2x. Plus 2 divided by 8, because we're multiplying 2 over 8, cos of 2x. And this goes to 0, so we just write nothing. And that's your integral, and don't forget to add on plus c. So that's one of the 3 stops that you need to know when a derivative goes down to 0, and that's how we can use it. We can simplify this down a bit, so we can know that's going to equal 1 divided by 2x squared cos 2x plus 2 on 4, 1 on 2x sine of 2x. 2 over 8, 2 goes into 8 once, into 8 4 times. Plus c. And we can probably take out, we can take out a 1 over 2. So you can say our final answer is going to equal 1 over 2. Chuck some square brackets in there. It's going to be 1 over 2. Since this is positive, we'll put this first up. So that's just going to be x sine of 2x, just to make it look a bit nicer. And then we'll put this in, plus 1 over 2 cos of 2x. So we've dealt with these, cross them out, then just the last one, minus x squared cos of 2x plus c. So that's how you solve that one, and we could probably simplify it down a little further if we wanted to, but no need. I think it's good, and this is definitely will get you pick up your marks in your exams. So we've covered two of the stops with the differential integral table, and let's move on to the third stop. This is the most tricky method to integrating by parts, and I'll show you why. And I want you to pay close attention because you're going to need to be able to pick this up so you're not doing integration by parts forever, because you will be if you don't pick up this little trick. So say you were asked to integrate ex sine of x dx. And what I want you to recognize is that you know ex integrates and differentiates to ex. It's never going to stop integrating or differentiating, even if you integrated or differentiated e to the x a billion times, it would still be e to the x. And I say this because you know it's never going to go to 0. And sine x is going to integrate to negative cos x, which is going to integrate to negative sine x, which is going to integrate to cos x, which is going to integrate to sine x, which is going to become negative cos x, and what I'm saying, it's never going to stop. So this is the next stop on our table. And I'll write it out the full way just so you can kind of see what I'm doing here. And essentially we want to stop when we get to a function that is the same as the original function, and I'll show you what I mean. So let's say we differentiate e to the x, really doesn't matter, it will work out the same. We integrate sine of x, and if you want to integrate e to the x and differentiate sine to the x, we should get the exact same answer. So it really doesn't matter. Try that if you want to. E to the x differentiates to e to the x. Sine of x integrates to negative cos of x. Negative cos of x integrates to negative sine of x. E to the x again differentiates to e to the x. And what I want you to pick up here, we've got to a point where these functions are equal. And this is what you need to recognize, because then we can just use basic algebra to solve this integral. Because we're not going to be able to do it by differentiating down to 0 or finding a row that we can integrate, because that's never going to happen. So this is how we would solve this kind of integral. Again, we'd start by multiplying down diagonally again, so that's going to be negative, and I'll write it out like this because I want you to see this. This is going to be the integral of e to the x sine of x dx equals, now we're going to start, that's going to be e to the x negative e to the x cos x minus e times minus sine plus sine, plus e to the x sine of x, and we're taking away, and this is what I want you to pick up, alright? Because this is a row that we can integrate, or we can't integrate it technically, but it's the same as the original function. So we're going to say that we can integrate this, because this is important. Take away the integral, because that's a minus, we're taking it away, e to the x sine of x dx. And we have now found two functions that are equal to each other. So we can bring this over to the other side, add it on, so we're going to have 2 e to the x sine of x dx equals negative ex cos of x plus ex sine of x. So we can now actually begin to solve this. we can divide this side by 2 to get rid of this integral. To get rid of the 2. So now we know that the integral of e, and we have to divide this side by 2 as well. So now we know that the integral is going to be equal to, let's write it as negative a half. Actually, we can factor some things out as well. So we can write it as integral will denote as ex sine x dx equals, that's going to become 1 over 2. And let's factor out e to the x, since it's in both terms. We factor out e to the x. Let's deal with sine x minus cos x. And don't forget to add on plus c. So you know your integral f of x equals a half e to the x sine of x minus cos of x. And don't forget to add on your plus c. So that's your third stop of integration by using the table. Is when you find a row that integrates that is the same as your original integral function. And it doesn't really matter about the constants. What you want to match is the variables. You want there to be the same, because you can take the constants out, but you want the variables to be the same, alright? Let's work on one more, and this one's going to be a little more tricky. So say we were presented with an integral of, let's just say, e to the 2x multiplied by sine of 2, let's just say 4. Let's spice things up a bit. Let's just do e to the 2x multiplied by cos to the 8x. And again, I want you to pause the video, give this one a go. We're going to have our differential integral table. Remember, pluses and minuses oscillating in the differential side. Let's say we differentiate cos to the 8x this time. And we're going to integrate e to the 2x. Cos to the 8x, using our chain rule, is going to become negative 8 sine of 8x. Integrating e to the 2x using our reverse chain rule, divide by the derivative. It's going to be 1 divided by 2 multiplied by e to the 2x. And you can see we have a cosine of 8x and e to the 2x. That's what we want to match. Forget the constants. We want to match the functions. So again, looks like we're only going to have to do one more row. So let's differentiate minus 8 sine 8x. That's going to become minus 64 cos of 8x. And integrating this is just going to become 1 over 4 e to the 2x. And what I want you to see is we have a row where we end up with the same functions. As I said, constants do not matter. You just want the same functions. That's all you want. So let's begin. So we're going to multiply down again. That's going to be half e to the 2x cos to the 8x minus 8 sine of 8x is going to become positive. That's going to be 8 over 4 e to the 2x sine of 8x. And our row, we're going to integrate this, and you can see that's a minus there, so the minus carries over minus the integral of, and the minus is just a constant, so just bringing it out with the integral. So minus, that's going to be 64 divided by 4 e to the 2x cosine to the 8x. I should also write up here that e to the 2x. Okay, so we can simplify this down a bit. 64 divided by 4 would be 16, so let's just simplify things down a bit. Have e 2x cos 8x equals a half e 2x multiplied by cos of 8x plus 4 goes into 4 once into 8 twice. That's going to be 2e to the 2x sine of 8x. 64 divided by 4, 16. We can bring the constant out the front. That's what we want to do. Minus 16. Then we'll have the integral of e 2x. So that's our answer. Well, not quite, but hopefully now you're picking up the pattern that, once again, we've ended up taking away the integral. And it's the exact same integral, but with the constant out the front. So we can add 16 of these onto the other side, then divide by 16, and we can solve for the integral. So if we're adding 16, it's like x plus 16x. Think of these as variables, if you like. So that's just going to become 17 multiplied by the integral of e to the 2x cos of 8x. It's going to be equal to, we can take out e to the 2x, and that's just going to be half cos 8x plus 2 sine 8x. And divide by 17. And that's how we solve our integral. So I'm just going to write this out in a nicer way. I think 1 divided by... So we know our integral f of x can be equal to 1 divided by 17 to the 2x. That's going to be multiplied by half cosine 8x plus 2 sine of 8x. And don't forget your plus c. So we're going to wrap the video up there. But I hope that was helpful, and that's essentially how you use integration by parts. I think the table method is far superior, as it really helps you not to mess up the signs with your pluses and minuses. It just gets really messy when you have big integrals like this. It's much better to use the table method, so that's the one I suggest that you stick to. And thank you so much for watching the video. In the next one, we're going to be talking about integration by u substitution. These are for some complicated integrals. We can make it a bit easier by substituting u in, but we'll talk about that later in the next video. But for now, just remember, Jesus loves you and I love you too. Bye.